Now, this video looks at integration problems where we have an integrand here and our denominator cannot come down to a nice factorization. We can't get it to a nice factorization. And if you have a look here, we can't factorize it at all. So what we've got to do is have a bit of manipulation involved. Now, we can't get down to nice factors, so it's not partial fractions. But if we can rearrange it so that we can get a perfect square. Now, you can see why in a moment. But if we have a look at our manipulation, completing the square on x squared plus 2x would mean we add 1 to it, which we got a 1. So decompose the 1 to be 1 plus 3. Which means we'll come down to x plus 1 all squared plus 3. Now, if we go to our table of standard integrals, that comes down to an inverse tan function, which is very nice. That's meaning we've got something that we're able to manipulate it down to get a function which can be integrated by our table of standard integrals. And that's what we're going to do with all these functions in this video. So we're looking to, there's another way of looking at our denominator. Can't get nice linear brackets, so we can't get partial fractions, but we can get a perfect square. So the next one here is again a little bit of manipulation needed, because we've got a 2x x squared plus 2x plus 4. Again, can't get nice factors there, so can't simplify down. We can simplify it a bit, because we're looking at this one and going, and hopefully we're looking at, well, it's 2x derivative, it's close to a derivative of the function over the function, but it's not quite, because it's only 2x. The derivative of x squared is 2x, but then we'd have the derivative of 2x, which is 2, which is not necessary, but we can add the 2, in there, which would mean, well, if we could, that would not be a nice log function. You can see it comes down to a nice integration of a nice log function. But to do that, we've got a minus 2 as well. Now, this is not going to be a log function when we integrate it, because it's now not a derivative of the function over the function. But we can see that we can manipulate it to get the x squared plus 1. So broken it down to x squared plus 2x plus 1 plus 4 plus 3, and it comes down to x squared plus x plus 1 all squared plus 3, which integrates to an inverse tan function. So we can do a bit of manipulation. We look at it first and go, oh, is it derivative function over the function? Because it's 1 degree less, so that's always an option, but it's not quite what we needed. So we have to go with that manipulation. This time we've got 1 over x squared, so it's not going to be an inverse. I'm not going to get a log function there because there's no x on top. So again, we're looking at it going, well, that's not going to give me nice factors. We can't do it that way, because it's not, it's even looking at our function there, it's not going to give us those nice linear factors that are going to work for us. And it's actually going to give us a situation where we'll get a, if we tried to factorize and get roots of that quadratic, we won't get any. It's because the discriminant on that, we get 16 minus 4 times 1 times 7 negative. So this is where we have to start to manipulate it a little bit differently, and we go back to that perfect square. So decompose 7 to 4 plus 3, and that comes to x plus 2 all squared and plus the 3, which is going to be an inverse tan function. The last one here is a little bit harder to get that perfect square. Again, we look at 1 squared minus 4 times 4, 2 times 5. Well, it doesn't come down to, it won't be able to factorize it. So then we'd be going, well, can we get a perfect square on the bottom and come down to an inverse tan function? Well, we can, with a little bit of work. So have a look. We factorize a half out, so 2 in the denominator. So we do that because we can't get a perfect square with 2 in there. So we get the x squared plus x on 2 plus 5 on 2. Now to complete the square, well, I need 1 on 16th. 1 on 16 would complete the square, because it will come down to x plus a quarter, because that's x, that's a half x, so it'll be x plus a quarter there, so a quarter squared is 1 on 16. And the 5 on 2 minus 1/16, well, that's going to give us 39 on 16. So that comes together to give me the 5 on 2. So there's our decomposition. And then we're at the point where we've got a perfect square plus the other term, which is going to integrate to an inverse tan function. So you got the half out the front, the 1 on the root 39 on 16, which can come down to root 39 on 4, and the x plus a quarter on top, square root of 39 on 16, which again would be square root of 39 over 4. So that's where the 4 starts to appear there, and the 4 goes up top, and 4 divided by 2 gives us the 2 there. So check that manipulation from that line to that line, just so you're understanding where all the numbers are coming from in terms of the 4 and the 2 there. So there we go. If you can't factorize it in any way, shape or form, even if they're really ugly factors, even if they're really ugly factors, you can get down and do partial fractions. But if you can't factorize it because the discriminant of the function in the bottom is negative, then you're going to have to try to manipulate to get a perfect square plus or minus a number. It's okay if it's minus a number because there is standard integrals that allow you to do that, but keep going back and checking that you can get something back into the standard integral form.